Dear friends, welcome to the next lecture on advanced thermodynamics. So in the last lecture, lecture number 30, we looked at condition for equilibrium and applied the condition for the case of phase equilibrium. So what we obtained is that at constant pressure and temperature, the condition for equilibrium turned out to be that the Gibbs function should go to a minimum, or dg should be equal to 0 for equilibrium, and dg should be less than 0 for any spontaneous process to happen. So whenever the Gibbs function decreases, the spontaneous process can happen, but the moment it reaches a minimum, movement to any side from the given equilibrium position would require an increase in dg, an increase in g, that is dg to be positive, and that is not permitted by second law. So that is basically what we saw. So the minimum Gibbs function is the state of equilibrium. So this is one thing that we saw. And then when we try to expand the condition, when we fix the pressure and temperature, then the dg, which is actually equal to v dp minus s dt plus summation of mu I dni equal to 0, or less than or equal to 0, is a condition for spontaneous process. So at equilibrium, you get a condition where summation of mu I dni is equal to 0 for a multi-component system. Now, if each of these components is in p different phases, alpha equal to 1, 2, 3, capital P, then what we found is that the summation of mu alpha dn alpha should give you the mu I dni for any given phase, any given component. And likewise, for I is equal to 1 to n, this can be there. So you actually get a double summation as a condition for equilibrium. Summation of I varying from 1 to n and summation of alpha varying from 1 to p of mu I alpha dni alpha equal to 0. So this is the condition that we had. So let's go back to the whiteboard so that it will be easier to visualize what I'm trying to say. Right. So the condition that we wrote was that for each species I, mu I dni is equal to summation from alpha is equal to 1 to p of mu I alpha dni alpha, and therefore if I substitute that into this expression for equilibrium, that is dg at t and p equal to 0, then it gives you a double summation I is equal to 1 to n, summation alpha equal to 1 to p of mu I alpha dni alpha to 0. Now also, when there is no chemical reaction happening, the number of moles of each species in our system do not change, and therefore dni is equal to 0. Okay. And the change in number of moles of each species would actually be a summation of the change in number of moles of each phase of the species. So dni, which is equal to 0, will actually have to be equal to summation over alpha is equal to 1 to p of dni alpha, and since ni is constant and dni is 0, this is equal to 0. Now between these two, you actually get equations that will be useful in finding out composition of multi-component systems if the corresponding values of mu's are equated at equilibrium. So then what we did was to take a pure substance for the simplest possible case, so that you don't need to do the outer summation because n is equal to 1. So it will only be the inner summation, which will be mu alpha dn alpha summation, is equal to 0 for equilibrium. So that is what we wrote. And when there are two phases in equilibrium, alpha is equal to 1 and 2, we said this is equal to 0. So mu1 dn1 plus mu2 dn2 is equal to 0. Okay. In addition, since the number of moles of the substance is not changing, but there is only phase change that might happen, so dn of phase 1 plus dn of phase 2 add up to 0 because the dn itself is 0, because n is constant, number of moles is constant. So if I substitute from here dn1 equal to minus dn2 into this expression, I'll get mu1 minus mu2 into dn1 is equal to 0. And since dn1 itself is an arbitrary change in the number of moles of a species, and even when there is some change of this that is happening, for equilibrium this has to be 0, so the mu1 and mu2 will have to be equal for this equilibrium. This is basically what we derived. This can easily be extended to multiple species, and we can say that mu1 equal to mu2 equal to mu3 is equal to mu p for each species. And when I have a multi-component system, in that multi-component system, for each species I'll be able to write this expression. So we got this, that is for species 1, mu1 1 is equal to mu1 2 is equal to mu1 3, etc., mu1 p, where the superscript stands for the phase and subscript stands for the component. Okay. Similarly for mu2, so mu3 up to mu n. So there are p minus 1 equations in each species, and there are n species, so n into p minus 1 constraints that are there. So in order to specify this state completely, total number of variables would be, since out of this n minus 1 are independent because they'll add up to the total number of moles of the system n, or the mole fractions of these would add up to 1, right? Similarly, in this one, so there are n minus 1 into p equations, because there are n minus 1 components that are independent of each other. The nth component is obtained by subtracting the summation of the mole fractions of the others from 1. Okay. So n minus 1 multiplied by, there are p phases. So n minus 1 into p will be the total number of degrees of freedom of this if there are no constraints imposed. But because in each of these n species there are p minus 1 constraints, that the mole fractions, the chemical potentials will need to be equal, we'll get p minus 1 constraints multiplied by n. So when I subtract that, I get the number of independent variables that need to be specified in order to determine the state of this multi-component multi-phase system. So if I do that, then I get this np getting cancelled. I'll get an n minus p plus 2 will be the number of variables that need to be specified in order to determine this system state completely. But that 2 is added because of temperature and pressure. So this is one thing that we said, and this is called the Gibbs phase rule, which we will be using today. The other thing that we said is for liquid vapor equilibrium, or any phase equilibrium for that matter, mu1 equal to mu2 or g1 bar equal to g2 bar for a pure substance. And therefore dg will be the same as dg1 dg2, because if there is any change, then both of them will have to change simultaneously. I just differentiate this, so I get dg1 equal to dg2, and each one of them will be equal to the v dp minus s dt for this respective phase. So v1 dp minus s1 dt will be equal to v2 dp minus s2 dt. So if I rearrange that, I get dp by dt at equilibrium of the phases 1 and 2 is equal to s1 minus s2 divided by v1 minus v2. And for a liquid vapor system, it actually becomes sfg by vfg. It can be in molar form or mass form. Both sides, numerator and denominator, the molecular weight can get cancelled, and you can write sfg by vfg. And since the phase change happens at constant temperature, usually for liquid vapor equilibrium, for example, this sfg can be written as hfg by t, because we can actually get from TdS is equal to dH minus ddP, and since the temperature remains constant in this, I can divide throughout by and temperature and pressure can remain constant during the phase change process. The VdP term goes to 0, so I'll get, let's write that here, TdS is equal to dH minus dP, and for a phase change process, temperature and pressure remain constant, so this goes off to 0. So if I get this, I get ds is equal to dH by T. So this I can write it as HFG divided by Tsat d bar Fg. So this is what we call as the Clapeyron equation for phase change. So these are the things that we had deduced in the previous class. So today we'll just take that discussion a little bit forward. You remember that we represented the chemical potential in terms of fugacity, because the chemical equilibrium seems to have values ranging between minus infinity to plus infinity, whereas the chemical potential, the fugacity would have values which are in a more finite range. Right? So if I use the definition of fugacity, I'll write d mu at constant temperature is equal to RT C of log F, and here it's a mixture, so I'll write an F bar. Right? So for any species I, which can be in multiple phases, if I write this, I'll be able to write mu I alpha, okay, minus mu ref for I. So I'll write instead of mu ref, I'll just write mu naught. So that is a reference state for species I, okay, which will be the same for all the phases. So this is the reference state is equal to, so this is integrated between the reference state and the current state. So I'll get, and it's a constant temperature isotherm integral, so it will be RT into log of F bar by F naught. Okay. So now this F naught of I is basically the reference state fugacity of pure substance, and this is the mu I alpha is the chemical potential of the substance as it exists in the mixture in phase alpha, and this is the reference state of pure I at chemical potential of the pure I at reference state. So the difference between these two, so basically you are integrating it from a pure substance I in reference state to substance I in phase alpha in the substance in the mixture. So this difference is equal to this. Now this can be written also for all the other species. So I can say this can be written for alpha is equal to 1 to n. So this will be F alpha. So what I'll find is that this is common. So I'll write the same expression for all the other species. So basically what ends up happening is for all alpha, it's basically only this that is different in the equation. All the others are the same. So if I say mu I 1 minus mu naught I is equal to RT log of F I 1 divided by F I naught or F naught I. And I can write the same thing for mu I phase 2 minus the same mu naught I is equal to RT log Fi in phase 2 divided by F naught I. and so on. So if I look at these expressions, this can be written for all species alpha is equal to 1 to p. So if I can write all of this, if I look at these two, then I subtract one equation from the other. Basically, what I'll get is since all of these are actually equal, so since at phase equilibrium, mu I1 equal to mu I2 equal to mu I alpha equal to mu IP, all of these are equal. So if I equate these, so this will get cancelled out and this F naught I would get cancelled out. So basically you'll find that Fi alpha, F1 alpha is equal to 2 alpha equal to F3 alpha. Okay. So as it exists in the mixture, the fugacity of species, what did I do? All for species I, the phase 1, 2. So Fi1 is equal to Fi2 equal to Fi3 equal to I alpha. Okay. So this is basically derived quantity from this. So if the chemical potentials of all the phases have to be equal for chemical equilibrium, phase equilibrium, then the corresponding fugacities of the individual species as they exist in the mixture will also have to be equal. So this is the next result that we get. So in order that if a system has equilibrium of phase, each species should have the same chemical potential in all the phases that exist in equilibrium. And similarly, each species should have the same fugacity of all the species as it exists in the mixture when the system is in phase equilibrium. Right? So this is the result that we get from here. There's one more interesting result that we can get from this one, that here we wrote this expression. So mu1 minus mu2 dn1, okay, because we said that dn1 and is equal to minus dn2 in a pure substance of two components, dn1 equal to dn2, right? dn2 equal to minus dn2. So I substituted for my dn2 as minus dn1. So I got a mu1 minus mu2 dn1 equal to 0. Now this is at equilibrium. So for a spontaneous process at this stage, this was less than or equal to 0. The equality applies for phase equilibrium and less than applies for a spontaneous process. So this result, we can take it to the current page and then just take a look at that. For a spontaneous process, okay. So right now we are just taking number of species equal to 1 and number of phases equal to 2. Okay, so you're just looking at two phase single component system. So you will actually have mu1 minus mu2 into dn1 is less than or equal to 0. Equal to 0 is for equilibrium. For a spontaneous process, it has to be less than 0. So what does this mean? So suppose there is change from phase 1 to phase 2 that is happening. Okay. So there is a spontaneous process which is, let us say, changing from phase 1 to phase 2. Let us say phase 1 is liquid and phase 2 is vapor, for example. So mu1, okay, so it's going from liquid to vapor phase. In which case, dn1 has to be negative, because there is phase 1 getting converted into phase 2. So dn1 is negative and dn2 is positive. Now, if I come here, if dn1 has to be negative, then this has to be positive so that the spontaneous process is feasible, which basically means mu1 is greater than mu2. Okay, so if change is happening from phase 1 to phase 2, then mu1 has to be greater than mu2. If the opposite is happening, let us say 2 to 1 is happening, then dn2 is negative and dn1 is positive, so this is positive. So in order to have this less than 0 condition satisfied, this has to be negative, which basically means mu2 is greater than mu1. So it appears from this equation that the spontaneous change is always from that substance that has a higher chemical potential to that phase that has a higher chemical potential to that phase that has a lower chemical potential. The numbers should all be in superscript. Okay, subscript here. So this is mu1, mu2. Here it is mu2. So this is another important result, that mu being the chemical potential, the spontaneous change of phase always happens from that phase which has a higher chemical potential to that phase which has a lower chemical potential at any given condition. And when the chemical potentials become equal, then the phase change stops to happen. So that is, the change from phase 1 to phase 2 would be balanced by the phase change from phase 2 to phase 1, so much so that there is no net dn1 or dn2, both of them go to 0, and this whole thing goes to equilibrium. So mu1 equal to mu2 and dn1 equal to dn2 equal to 0 is what happens in equilibrium case. So when there is a minor departure from equilibrium, this equilibrium always is restored by movement from the higher chemical potential to lower chemical potential, is what this first and second law combined equation. So that is the other corollary of the equations that we derived in the previous class, which I wanted to just highlight. Now let's look at the calculation of these fugacities, starting from the simplest possible cases. So evaluation. So in order to understand this, we'll also need to do a little bit more exercise on what we have done, how we calculate fugacities of pure substances. We looked at calculation of fugacities of pure substances for real gases. For real gases, we use the real gas equation of state, and so we were able to calculate the fugacity from the definition of the chemical potential. Let's go to the corresponding page, then we can recall that chapter when we calculation this. Yeah. Yes. Yeah. So when we defined the fugacity from the basic definition, and we said that mu I minus mu I star, which is a reference state, is integral from P star to P of V dP. Now we then said that the fugacity can be evaluated using this, where this is for a mixture. Let's go back to the pure substance page. So that is where we this. Yeah. So this is the method of calculation of fugacity. So we said that if P of V is in a functional form available, then we can integrate. So this, we said that if we had any of the equations of state, such as van der Waals equation of state, or Redlich-Kwong equation of state, or Lee-Kessler equation of state, then for all of those equations, P as a function of V is available, so we can integrate. Otherwise, we said that from the generalized compressibility chart, which is basically typically applicable to pure real gas, right? So we said how to evaluate the fugacities by using either the compressibility chart, or from that you can actually get the fugacity, generalized fugacity chart, or from the enthalpy and the entropy corrections. Log of F by P is equal to this expression in terms of the enthalpy and the entropy corrections for that real gas. Now, this is something that we had already done, but we'll need to also see how we evaluate the fugacities of solids and liquids. Because when we look at phase change, we would be looking at phase change from liquid phase to vapor phase, or vapor phase to liquid phase, or solid phase to liquid phase, and liquid phase to solid phase, and so on. So we'll also need to know how to evaluate fugacities of liquids and solids before we go further. So real gases, we got generalized fugacity chart, or generalized enthalpy and entropy correction charts. And using that, we calculated the log of F by P is equal to. So this is something that we had already done. So this is pure real gases. Okay. So what do we do for pure liquids? Okay. How do you evaluate the fugacity of a pure liquid? Let us try to understand that. So what is observed is that most pure liquids or liquid solutions, okay, sorry, talk about most liquid solutions and solid solutions. What do we understand by solid solutions? For example, you look at the iron steel phase. What we have there is a solid solution of carbon in iron. Right? So that is how you get this, or you get the solid solution of manganese in iron. You get stainless steel and so on. So those are examples of solid solutions. And liquid solutions, we already are more in a better position to visualize. For example, water ethanol mixture is a liquid solution. Water glycol mixture, what we use in automobiles as coolants, is a liquid solution, and so on. Now, most liquid solutions and solid solutions, at least approximately obey Lewis and Raoult. That is, they behave as ideal solutions. Not all, but most liquid and solid solutions do behave like this, and therefore we should be able to write Fi bar is equal to Xi by in the reference state, okay, in the pure state. So Xi Fi. So Fi bar in the solution is at least approximately equal to Xi Fi. This is the Lewis and Raoult rule, and this is applicable to most liquid and let's not say most, but at least say many. It will make life easier. Many liquid and solid obey this Lewis and Raoult rule. So this is more difficult to measure, because this, we know, requires the measurement of change in P minus V for each species at various conditions, and then integrated from P star to P, dP. Right? So this is the thing that you get, but this is more difficult to measure. But this one is easier to measure, because this can be obtained either by the fugacity charts or by extrapolation of the fugacity charts. or by using any specific equation of state that might be available for the substance P as a function of V. So this can pure substance Fi can still be easily evaluated, and therefore commonly if this is obeyed, then life becomes much easier. Right? So what we can do is then we can use methods by which pure liquid fugacities are evaluated to evaluate the fugacity of substance as it exists in the mixture. So that is one. The next one is that at any given state, actually this can be obtained for a pure substance. RT D log F for a pure substance is equal to BEP is something that is known, and for a pure substance, this can be integrated from a reference state to the current state. Now, this reference state can be a state where the substance, the liquid, let us say, for example, is in equilibrium with its vapor. Okay, so then at liquid vapor equilibrium at pressure P, let us say. Okay, so at some pressure P, or let us say P ref, at some pressure P ref, the liquid vapor equilibrium would say that at that condition FL is equal to F, because when liquid and vapor are in equilibrium, F and FL and FV at that pressure are equal. So if I take that as the reference state, and so if I call this as FL naught and FV naught, where this is at sort of, let's say P ref, let's call it as P naught reference state. So this, then I can integrate this expression from pressure P naught to the current pressure P by integrating this. Then I'll be able to get. So if this I integrate as RT into log of F bar by F naught L. So this is the equilibrium state in the liquid phase. I integrate from the equilibrium state to the current state, where the state is this is F bar, and here no, it's why F bar, it's a pure substance, so I'll just write F. Okay, so in liquid state at any given state F by F naught. Okay, now this would actually be equal to integral from P naught to P of V into EP. Now this P naught is basically at this P naught, basically we are looking at saturation. So this is actually in some state the saturation pressure at the same temperature T, right? So okay, now at the same temperature, so pressure is equal to P sat actually. Okay. So at that condition we say FL FL equal to FV at saturation. So instead of the 0 I can actually have saturation here. So you're actually integrating from the reference state to that state. So this will be So this is P sat to P this. Now, since for a liquid, this V bar does not vary much with pressure, I can take that out of the integral. So this will become actually V bar into P minus P sat. Right? So this is basically what we will get. So log of F by F sat will actually be P into P minus P sat divided by RT. So let me get that RT from that side to here. So I'll remove this RT here and write it on this side. So this will be 1 over RT. So this is basically what we get here. And if the pressure at which we are evaluating this fugacity is not very largely different from Psat, if it's a comparable pressure, since this small v will be a very small value for liquids, this correction actually can be neglected. Okay? And we can say F is approximately equal to FL sat. So for P of the order of Psat, the V bar into P minus Psat divided by RT is actually called the pointing correction. Is approximately equal to 0. So only when the pressure P exceeds Psat by a substantial amount do we actually have to worry about this. But otherwise, the pointing correction can be neglected. Then in that case, log of F by F sat of the liquid is equal to or approximately equal to 0, or F is approximately equal to FL sat. And since FL sat is also equal to V sat, because at saturation the liquid and vapor have the same fugacity because they are in equilibrium, so then this FV sat can be evaluated, because this is in gas state, it can be evaluated using the generalized fugacity chart at the given pressure and temperature. That is the saturation pressure and the same temperature. So this F can be evaluated from the fugacity chart, and then this F can be determined. So for liquids, we can say you can actually, at any given temperature, so for liquids at any given temperature, I actually integrate from the saturation state at the same temperature to the current state, and in that case, if the pressure is substantially larger, then the correction using pointing correction is evaluated, and this is used for this. So this is not equal to 0, but equal to the pointing correction. But if the pressure is not very much different from the Psat, then we can actually use F to be approximately equal to FL sat, which is also equal to FV sat, which can be evaluated from the generalized fugacity chart. So in the same fashion, for solids also, you can actually start from the triple state, where the solid and vapor been in equilibrium, and then integrate. But if the temperature is different from the triple state temperature, then you may not be able to integrate from the triple state, in which case your integration will need to happen from the saturation conditions of phase change of solid to vapor, if at all it exists at the same condition. Or you get the solid liquid equilibrium. The liquid you get from the liquid vapor equilibrium using this relationship, and then you can use for solid liquid equilibrium also, you will have Fs at saturation will be equal to Fl at saturation. In this case, the saturation is of solid liquid. In this case, the saturation is of vapor. So you can actually evaluate, say for example, I want to evaluate at some temperature at which there is no sublimation happening, but there is a transition from solid to liquid and then from liquid to vapor. Then at the same condition, I can actually get from the liquid vapor equilibrium state the fugacity of the liquid, and then equating that to the solid liquid equilibrium state, I can get the solid fugacity also. So the solid fugacity is also evaluated in this fashion. So Now, in liquid vapor equilibrium, we know that FL sat is equal to FV. The liquid and vapor fugacities are actually equal, and if these behave like ideal solutions, if both liquid and vapor behave as ideal solutions, okay, then for the multi-component mixture also, the pure substance relations can be used, in which case I'll have Xi in liquid phase into F fat L at the liquid phase, okay. Um, is equal to okay, Xi in vapor phase into F sat of the vapor phase in that condition. So for liquid vapor equilibrium, in the case of a multi-component mixture, this FL bar and FV bar are equal. Now this FL bar in ideal solution can be written in terms of this using Lewis-Randall rule, and FV bar can be written using this using Lewis-Randall rule. Now, in the special case where vapor behaves as ideal gas, then the FV sat is equal to P sat. Okay, so then we can actually use P sat here, and okay, so this is the expression that you get, and in the case where sorry, in this case, this will actually be equal to the total pressure, not P sat, but P, and FL sat will be approximately equal to P sat, obtaining from this expression where this FL is equal to FV at the saturation condition. So this becomes equal to P sat. So the this equation eventually comes to XL of species I into PI sat is equal to Xi in the vapor phase multiplied by P. Now, this is the expression that we will get to, and this expression is called the Raoults law. So Raoults law is applicable when the liquid as well as vapor are behaving like ideal solutions. In fact, the vapor actually behaves as ideal gas mixture, and the liquid behaves as an ideal solution. Then the Poynting correction goes to 0, and therefore the F of the liquid actually becomes equal to FV sat, and since it behaves as an ideal gas, this will be P sat of the vapor. Whereas for the vapor mixture, this F sat, the F of the vapor, so in the wrong things here, L is equal to V in the mixture. The mixture, the conditions is not the same as the saturation. So this is FL is equal to FV. This FV becomes equal to the pressure of the mixture of gases on the vapor side, whereas this FL becomes equal to FL sat according to this expression, okay, which is nothing but P sat in the ideal gas limit there. So you get XIL into P sat is equal to XIV into P. So this is nothing but the mole fraction of species I in the liquid phase. The liquid phase is a mixture of n different species, and the vapor phase is also a mixture of n different species, but it has a different mole fraction. This XIV, this XIL and XIV are related by this relationship, okay, PI sat and. So this is the expression that you get, and this is called the Raoults law. The Raoults law is basically obeyed when the liquid mixture obeys ideal solution and the gas mixture obeys the ideal gas law. Okay. So now if I have n species, that is n component mixture, for each species I will be able to write the Raoults law. So I'll get n Raoults law statements, which says that XIL into PI sat is equal to XIV into P, where P is the pressure of the system, which is actually the pressure of the vapor mixture. The PI sat is the saturation pressure of the individual species P, individual species I at that temperature. So now this I can write for each I, for I is equal to 1 to n. Okay, so you already have n variables that are available to you. So if I say f is equal to n minus p plus 2, okay, now out of which there are n equations which are already specified here. So I'll be able to evaluate n unknowns, and this is a two-phase system. So this P is 2 because you are looking at liquid vapor equilibrium. So the number of variables that need to be specified, f is equal to n plus 2, and if temperature and pressure are specified, then this 2 is already known. So you get f is equal to n. So you need to actually have n more equations in order to get the composition. So if I take a simple case of two component, two phase system, then f is equal to 2 minus 2 plus 2 is equal to 2. So there are only two the variables that need to be specified. So if T, P are specified, if T, P are specified, so these are two variables, T, P are specified, then composition of liquid and vapor mixtures can be evaluated. So this is a very significant result, which basically says that suppose I have ammonia water mixture, okay, and I specify the temperature and pressure. So I'll have a vessel in which, let us say, there is liquid, there is vapor. Okay. So the liquid has water plus ammonia. The vapor also has water plus ammonia, but the compositions are different. So you have X water and X ammonia in the liquid phase, and here you have X water and X ammonia in the vapor phase. Okay. So there are four unknowns: X V here and X XV here, XVW and XVA, and you have XLW and XLA. There are four unknowns, and there will be four equations that you can actually specify from the conditions that Okay, two component, two species, two phase, at constant P, example ammonia water. Okay, this is something which is commonly used in refrigeration, Gallina cycle, and so on. So then, if temperature and pressures are specified, then you have two Raoults laws which can be specified, saying that X water. Let me not write water. We just write 1 and 2. Let us say ammonia is 1 and water is 2. Okay, so I say X1 liquid, okay, into P1 sat at the given temperature is equal to X1 vapor P. And similarly, X2 liquid into P2 sat at T is equal to X2 vapor into. So these are the two Raoults laws that I have. In addition, I can also say in the liquid phase, X1L plus X2L is equal to 1. And in the vapor phase, X1V plus X2V 1. So these are four equations, and I have four unknowns, X1L, X1V, and X2L, X2V. So I can actually solve for these four variables and determine. So what will I get? For solving these, I'll just substitute these into this and eliminate X2 and do it. Then basically I'll get X1V is equal to X1L into P1 sat divided by P. Okay. And this is also equal to the P is basically the two partial pressures put together will be X1L P sat P1 sat divided by X1L P1 sat plus 1 minus X1L P2 sat. Okay. So this is total pressure. The total pressure is basically X1 P1 sat plus X2 P2 sat. So this is that. So X1V is done, and then X2V is equal to 1 minus X1V. And once this is done, you can actually calculate the quantities. So this is the expression, and generalizing it for a multi-component system, XIV is equal to XIL into PI sat divided by summation of XIL PI sat. This is something which we can do, and with that we can actually evaluate this. So these four equations and four unknowns will actually help us to solve all the four cases. If P1 sat, P2 sat, and the temperature is known, so P1 sat and P2 sat can be given, and P is known, then these are four equations and four unknowns that can be solved. So we'll stop it here. We'll actually be able to use this for various applications. One of the applications, of course, is determining the properties of liquid vapor mixtures, which are behaving like obeying the Raoults law, and calculate their properties and finding their proportions, because when you heat or cool ammonia vapor system, one species condenses more than the other, and therefore there is a change in the composition which can be evaluated using this. You also have solute-solvent relationships, particularly when I have, for example, hard water, and I'll need to remove or solute from it in order to make the water softer. Say, for example, desalination of seawater to get soft water, or using the reverse osmosis to get clean, drinkable, purer drinkable water with less dissolved solids as compared to the brackish water that we get from tube wells. Then these methods, this approach can be used. So in the next class, we'll look at a couple of examples of these, so a couple of applications of the system, and understand how to solve those systems. We'll stop here in